Hello AP Physics students, this is the IHS Physics Club, here to present you Unit 6 of AP Physics A, Simple Harmonic Motion. So what is simple harmonic motion? Simple harmonic motion is motion that oscillates back and forth. So how do you tell if an object is going through simple harmonic motion? Well, for an object to undergo harmonic motion, there has to be a restoring force proportional to the displacement of the object. For example, if a ball in a pendulum is swung 1 foot to the left, there has to be a restoring force that pushes it back to the equilibrium point and then 1 foot to the right. And it keeps on repeating the process going left and right to ongo simple harmonic motion. So we can use the equation F equals negative kx to represent the restoring force is proportional to the distance, which in this case is x. The negative sign in the equation represents the fact that it wants to pull the object back towards equilibrium, which is why we call it a restoring force. Keep in mind that this only refers to springs and pendulums, not for a ball bouncing up and down.
Okay, so now that we have already explored what simple harmonic motion consists of, now we can really dive into the differences between a spring and a simple pendulum, both of which exhibit SHM. So one thing to be careful of is their angular frequencies. And this is the mathematical expression where the spring and the pendulum have different numbers. So the spring follows the angular frequency of square root k over n. And k, remember, is the spring constant, while n is the mass of the object on the spring. And now this is assuming the spring is ideal or the spring doesn't have any mass, which will probably be the case in most of your problems. The pendulum follows the angular frequency is equal to square root g over L. Now, g is the gravitational constant. It's not always on Earth. Say you have a pendulum on the moon. Well, g is going to be a lot different. In fact, 1/6 of the value of Earth's, right? So take that into account. And L is simply the length of the pendulum. Notice how these formulas aren't too complicated. You don't have to take into account many other factors, right? Basically, just some key characteristics that you can't really modify if you were to make a physical setup of the object. And also note that when we talk about angular frequency, we're basically saying we're talking about the value times period is equal to 2 pi. So even though you might not hear the term angular frequency, which is denoted by omega, by the way, you can use that to solve for period because all you need to do is divide both sides by angular frequency in this formula. You get period is equal to 2 pi over the angular frequency, right? So the period for the spring would be 2 pi square root m over k, and the period of the pendulum would be 2 pi square root L over g. That's just something to take into account. And if we talk about regular frequency, which basically is not the angular version, it's the linear version, frequency itself times period is usually equal to 1, right? So just be careful of these little details, intrinsic deviation from one another, and yeah, we should be good for the problem that involve them. And last thing to remember is if you're not talking about small angles for a simple pendulum, if we're looking at a physical setup, real life setup, where it's not like 15 or 20 degrees or less from when the pendulum was initially released, then amplitude or the distance the pendulum is from its equilibrium position will also factor in when because there's more complexities involved. Obviously, when you're deriving these formulas for period, angular frequency, etc., you're going to have to make a bit of simplification, which is why it allows us to usually cancel out stuff like amplitude and all those other factors, because at small angles, they usually don't play that much of a role. They won't change the result by much. But if we were to actually solve the equations, prove everything out again, then yeah, you would have to take into account the angle, the amplitude, essentially, if you're not going at small angles. So if it's a larger degree, like say than 15 degrees, just take that into account on the exam if that does happen to come up. Now let's take a look at the conservation of mechanical energy within a simple pendulum system. So on a trajectory of the simple pendulum, as you can see here, we have the different places denoted where the kinetic energy and the potential energy reach their maximum. And it's important to be conscious of these facts that, for example, the kinetic energy is the greatest at the bottom of the pendulum's trajectory, which is obvious because it's going to be moving the fastest throughout the middle of its path, right? Especially as there's less height there, so there's less potential energy, and thus more of that potential energy is converted to kinetic energy. At the same time, potential energy is greatest at the highest point because there is the most height. As you know, potential energy is directly proportional to the height, and that therefore all of this kinetic energy is going to be converted to potential energy. In my opinion, just looking at the maximum potential energy is simpler because think about it. At the very top of the pendulum bob's motion, it's going to stop for a split second, right? And it's going to start going back down. Well, during that split second, its instantaneous velocity is zero. Therefore, at that point, its kinetic energy is also instantaneously zero. So where does all that energy go? Well, it gets converted to potential energy, correct? And that means that the conservation is satisfied and the kinetic energy therefore would be basically zero and start increasing as the bob falls back down. So obviously we've been looking at the ideal situation and scenarios thus far. And a real life scenario to really just think about and try to wrap your head around is a damped harmonic oscillator. Now, this is just a fancy name for a pendulum or a spring, for example, that undergoes harmonic motion and, however, experiences some effects that kind of dampen its motion. Essentially, it starts off all right, and then it gets slower and then smaller motion because of non-conservative forces like friction or air resistance or something like that, which causes its period to change variably. And note that while we may not get these types of questions on, say, the AP exam because they're just too complicated at this point to really even think about, it's still good to know that that's why in real life, if you're holding a pendulum and you let go, there's a reason why it wouldn't go on forever, right? And this you can kind of use it to explain that. Air resistance opposes the motion. Every time it swings around, it decreases its motion just by a little bit, a little bit, a little bit. Now all those small amounts start adding up, and that eventually causes the whole thing to just stop after some certain period, right? So just be careful of that as well. And that could be pretty much all that is really core to the understanding of the simple harmonic oscillator. As always, thank you so much for your support, for watching our videos. If you have any questions, make sure to reach out to us. We'll be happy to help at this IHS on Remind. And that's all we have for today's lesson. So thank you again, and see you for our next review.